We would like to welcome you to our Zonotip webinar. My name is Ali Reza Aklagi. I am joined today with my colleague Chris Udell.
Hi and welcome.
We both part of the product management team at Proceq. And as I highlighted earlier, today we're going to concentrate on our Zonotip ultrasonic thickness gauge, flaw detector. And mainly we're going to kind of go through the functionality of the device, suiting various different applications. We have got several different applications lined up for you. We're actually fairly excited. This, as far as the application concerned, this webinar, we have a full bag for you. During the webinar, you may have questions as we go through each section. Please use the Q&A box. Send us your questions, and as relevant, we will go through them and try to address them where appropriate. If not, at the end of the webinar, we have a dedicated section where we go through every single question and make sure we cover them all. So on that note, let's have a quick look at the agenda today. It's pretty much the same as what you have received with your invitations. And like I said, we're going to go through each section and cover the topics for you. On that note, let's begin our session. We're going to basically concentrate on what comes out of the box and different Zonotip models.
We've got the Zonotip here. Here's the device. And it comes with, well, Ali will tell you what the difference between Zonotip and Zonotip Plus is.
Sure. So basically, as Chris mentioned just now, we've got both of the devices set up here. The main difference between Zonotip and Zonotip Plus is the fact that with Zonotip you have the standard twin element transducer at 4 MHz, and with the Zonotip Plus you have, in addition, the single crystal 2.5 MHz transducer and the A-scan functionality. We will cover during the applications both standard mode for thickness measurement, memory mode, and of course the A-scan. Just as an introduction, and just before we start our main sort of topics, Zonotip is very much self-explanatory when you want to set it up. Even as for the transducer, everything is color-coded. So in this case, in order for me to start using the device, all I have to do is just follow the color-coded wires and connect my device again with the wires to the right connection. And there we go. Our device is basically switched on. We also have to go through a couple of simple procedures which we will cover for you later as far as zeroing and calibration of the device on the particular material. This is obviously very important. Both myself and Chris have some good examples here that we will show you. Moving forward, what we need to obviously highlight first is how the ultrasonic device works. The idea behind it is fairly standard. It's basically the beam that is generated and travels through the component. What Chris is going to do is going to kind of break that down for us and give us like an overall overview of how we translate this information into the material properties that we would like to define.
Yeah, thanks, Ali. As you mentioned, I will first mention, how do you get an ultrasonic beam generated? Here, for example, is our single crystal probe, and what it contains inside is a piezoelectric crystal. And the Zonotip sends a pulse to this, a voltage, a square wave, as is shown there. And that reduces the size, expands the crystal, when it's applied, expands the crystal when it's applied, and when it's removed, it contracts back down to its normal dimensions. If you do this repeatedly, then you will get an ultrasonic beam generated. Now, if you get any reflected ultrasound waves back, this contracts the crystal, and that also then gives the Zonotip device a voltage. This depending on the intensity of the sound received back. Now the Zonotip will then look at the time and the voltage that's received back, and then display this as a thickness. Before the result is displayed, it's converted into thickness, and that's because you need to enter the material velocity first, and that's the simple conversion it does. Ultrasound travels in straight lines, and it will be either reflected, which is shown in the diagram on the left below, refracted, which is not really the case in thickness gauges but other devices, and attenuated, which is shown on the right below, and that depends on the material properties there. Now, what you also get with a single crystal is a dead zone, what we call term as dead zone, and that's where the probe is ringing from the transmit pulse, and it's not ready yet to receive any signal. So what that means really is that you can't measure very close to the surface with a single crystal. With twin crystal it's different, but we'll mention that later.
Fantastic, thanks, Chris. So as Chris highlighted over there in a quite nice, detailed manner for us, when we transmit this ultrasound, in return we receive multiple echoes. These multiple echoes pretty much form the A-scan display for us. One thing to highlight here, each of these echoes can be used to define the thickness. However, when it comes to measuring thickness, in many cases you'll be able to take the average of multiple echoes, and in fact our Zonotip in the normal mode, when appropriate and possible, does that for you automatically. So it calculates the thickness based on an average of 3 echoes, for example. That's a very good advantage of Zonotip over some of the standard sort of thickness gauges. In addition to that, like I said, you'll be able to utilize the A-scan and manually move the gate around to the peak that you need. In this case, we're showing you some different peaks, and take the measurement from that particular peak. And again, by having the A-scan capability, that allows you to overcome various different applications. We've got some great examples for you here. So we highlighted earlier the Zonotip comes with 2 transducers, single element and dual element. Chris got them like up in the air for you. So what Chris is going to do is going to give us, from his experience, some real sort of examples and ideas where we end up using perhaps a single crystal over a dual crystal and vice versa.
Mm-hmm. So yes, as you mentioned, these are the 2 probes packaged with the Zonotip Plus, and they will cover the majority of all standard applications from what you found. You would use the twin crystal if you've for near surface flaws. As mentioned before, it doesn't have a dead zone. What you get is a small area of no coverage due to triangulation, but it's much better at detecting near surface flaws. So it's perfect for thin and flat material, for example. The disadvantage of this is it's a little bit bigger than this one. So if you've got access problems, or you need a lower frequency, which I'll come into later, then it's better to use the single crystal one. And because of its small footprint, you can also use this on curved surfaces like very small diameter pipeline.
Fantastic. Thanks, Chris.
So yes, if I mention now, this is the effect of frequency. The 4 megahertz transducer and the 2 megahertz transducer we've got. The 4 megahertz higher frequency won't travel as far in the component, but it does offer better resolution. So you've got to balance it out really of which we want to choose. If you want to go down deep into a component, use the lower frequency, and then vice versa for the higher frequency. So you can see the example here that sometimes because of material scatter, you might not be able to reach the target as shown by the twin crystal there. With the low, if you drop the frequency down, it can penetrate more, so that's good. And that's especially important with high attenuation materials, just like rubber,
plastic,
for example. So it's important to consider the size and of the defect and the geometry you're looking for, really.
So for example, if you're looking at, let's say, true code measurement, whether you're dealing with plastic, rubber, or possibly paint, then this is the time you probably may want to use a lower frequency.
Yeah. The maximum testing distance for both devices is 300 millimeters in steel. Mm-hmm. And when measuring on curved surfaces, if you're using the twin, you should make sure it's aligned around the center line to get a good signal from both the transmit and receive elements. One of the main factors to consider, though, is if the front surface and the back surface are parallel. If you've got some area where the signal, the component is not parallel, the sound will bounce away and won't be received. In some cases, it will be received very low, or the worst case, it won't be received at all. And then you can't use a thickness gauge for that.
Great, thanks, Chris. You know, when it comes to ultrasound inspection, this type of measurement, similar to any other test principle, even out of the ultrasound sort of let's say area, we always need to make sure that our instrument is verified and ready to do the test. When it comes to Zonotip, it takes advantage of this very user-friendly, easy-to-use interface to what we call to zero the device. And this is necessary prior to obtaining your velocity and obviously starting the test. How it's actually done is very simple. There is a built-in test plate in the front of your Zonotip. And like I said, if you just simply follow the few simple instructions with the device, you'll be able to zero your probe, basically compensate for all these cables and connectors, and then go ahead, define your pulse velocity, and do your test. And like I said, with Zonotip, anytime you disconnect or reconnect switch probes, you will have to select the particular transducer that you've connected and go through the zeroing process. We will actually cover that for you right at the beginning of the application side before we start the application. Let's say we've done the zeroing process and now we want to go ahead and do our test. Although there are several different material velocities pre-programmed in the Zonotip device, it's always recommended, as I said before, to define your material velocity before you start your test. And this is like a game performed really, really easily, really quickly. You just have to follow the simple structure on the device and define this material velocity. Always bear in mind that there are other conditions also influencing your material velocity, things like temperature or surface condition. One of the things that is fairly common, and we were actually talking about this a few days ago, is basically the amount of coupling paste that you apply on your reference sample and your real sample that you do in the test, and also the pressure that you apply. That makes a difference. And we discovered, what did you say? How much?
You can get up to 3 dB difference in your amplitude,
which
received.
is significant, really, and that will affect your thickness measurement to a large degree. So it's always good to consider these little side notes. Okay, now we talked very briefly on how a scan is displayed and how it's achieved with Zonotip. What Chris is going to do, you're going to break that down for us, how we then use the information that is displayed to us as a scan to define these material properties and characteristics that we are after.
Yep, thanks. So as Ali mentioned, an A-scan is essentially a plot of received amplitude versus time. This time is then converted into a distance using the correct material velocity, and that's why it's so important to calibrate exactly as your component conditions are. And then one of the main ways of analyzing the data is actually to monitor the backwall echo. And this here is, for example, if you've got a layered structure with bonding and you're checking the bonding of the thing, of the component, then you can get an indication on the bonding if the backwall echo is high, for example, and if the bonding is reduced, is inadequate, then the backwall echo will reduce. Another application for using the A-scan is actually to monitor the signal from any indication you get. And we did an application about a month ago where we were looking at some plate material which had a number of indications. When you use the A-scan function, you could see that a number of these indications were from porosity. And you can see in the top right drawing there, this is a typical ecodynamic envelope you get from porosity. And what we weren't really interested in that, we were looking for delaminations. So the A-scan function can really help you to characterize the defects and reduce the number of false calls, because we didn't want to report the porosity. That was always in there.
Sure.
So you can characterize quite well there. Another advanced method you can use with the A-scan is to size the defect as well. So you can use methods that are available in standards such as 6 dB drop methods.
Fantastic. Thanks a lot, Chris. So, what hopefully the sort of overview we've given you from what comes in the box with Zonotip and the sort of a possible setups have been useful. Before we go into our application side of things, one thing I'd like to highlight is that obviously we have taken certain number of application that we feel has a broader sort of range across different industries, but we always bear in mind these sort of techniques can be utilized for different type of application at the same time. Both Zonotip devices comply obviously to the international standard. You got the ASTM E797 and the BS EN 15317. One of the things that's always been our mission at Proceq is not just to supply an instrument, but also provide the know-how and the technical support, especially when it comes to application. So today, as highlighted earlier, we're going to kind of show you some nice common applications for Zonotip and Zonotip Plus. But at the same time, if at any time you feel like you need some clarification in a particular application, please feel free, contact us at Proceq or contact the nearest subsidiary to yourself, and we will be more than happy to look at your application and make the sort of appropriate recommendation to you. Now, the applications that we kind of picked for you today is pretty much based around sort of pipe inspection. What we're going to look at is some basic thickness measurement. We're going to look at some true coat measurements. Then we kind of look into delamination, some corrosion and erosion sort of inspection. And hopefully that gives you some good ideas about how you can utilize Zonotip. On that note, what I'm going to do before I go to the demo table and I start zeroing my device and doing a quick calibration for steel and show you the sort of a corrosion example that I got here. I'm just going to quickly talk about the bonding and how easy it is to identify that with Zonotip. In the first case, when we kind of have a good type of bonding, it's always common to see a very small echo and the larger echo at the back, and that means most of the ultrasound is traveling all the way through. And when you're dealing with like a poor type of bonding, it's actually common to see a larger echo before the sort of a back wall echo. That means not majority of the sound is not in fact traveling to the back wall, and that indicates the bonding is not necessarily great. When we're dealing with the erosion, it's common to see an echo and then a scatter of multiple echoes, and that indicates that there's possibly something wrong in that area and requires more inspection. On that note, I'm going to go to the demo table that we've got for you here. And then the first thing I would like to do is switch my device and start the demo. So first thing I need to do, I need to tell the device what probe I've connected to it. As you can see over there, I'm going to choose the 4 megahertz transducer. It's going to tell me make sure there's no coupling on it and enter. Next step, it will ask me to apply some coupling paste, and as you can see over here, and place it on the test plate on the front and then enter. This is pretty much the zeroing process. And then I press OK, and I'm good. Coming back out of the device, it will take me straight to the main menu. Going back to the menu, what I would like to do now is do a quick calibration on my steel sample that you can see over here. So as you can see, we got a predefined steel sample. So by placing the probe and then follow the instruction on the screen, you'll be able to define the pulse velocity for your particular reference sample before you begin your test. Now, going back to the example that I've got for you here today, as you can see, there is significant amount of corrosion for this particular pipe that I've got here. So, first thing I'm going to do, I'm going to apply a small amount of coupling paste and start the scanning process. As you can see, I've got a peak right about there. As I move this across my pipe, you can see how the peak actually changes and comes back. And at the same time, it also tells me how deep is this particular flaw or crack or particular corrosion area is within my sample. And it's really easy to identify applications and problems like this. What Chris is gonna show you now is pretty much a very straightforward standard application for Zonotip, which is basically the true thickness measurement and how easy it is to perform that.
Sure, thanks Ali. What I've done is I've already zeroed and calibrated the device. We use the stepper block, it's steel. What I'm going to test is the thickness of this pipe here. This is a common application for manufacturing, for example, where you need to verify that the thickness of the pipe is to standard and to specification within tolerances. So you can see with this, before I start, I can add couplant to the probe, and I can verify that my machine is working. So you can see there I'm getting a reading of 10. And if I move it down here, I get 7.5, for example. So that's verified on 2 points on this stepper block. Then I can move over to the pipe, keeping the crystal in the right orientation. And you can see there I get a reading of 8.1 millimeters. So that's the thickness of this pipe.
Thanks, Grace. Great. Okay. Well, next application is actually really common application, isn't it, Chris? This is actually a true code measurement.
Now, this is a through code measurement. Here, what we've got is a coated sample of a pipeline. We've got this plastic or rubber coating, but we don't actually need to know that using a special function on the Zonotip, because we can measure the thickness of the steel below that, and it will ignore the thickness of the coating.
And it's important to mention that the steel that we got under that rubber coating is basically it's the same material as our reference step block. So our calibration remains the same.
Yeah, exactly. So what I use is the multi-echo mode of the Zonotip, which is you change the mode by pressing this, and I'm in the A-scan mode here. Again, I add some coupling to the probe.
The importance of coupling.
You need a lot of it. And what you've got to get is 3 peaks in the gate. So you can see there we go. It's measuring 8 millimeters, 8.1 millimeters. And that the whole thickness of this is 14 millimeters. So you've got a 6 mil layer of coating on that, and it's just measuring the thickness of the steel below that.
Completely disregarding the rubber on the top.
And what it does is it does that by subtracting the first echo from the next 2 echoes, so it doesn't matter of the material of the coating.
Absolutely. A lot of time you might have to do such application manually, but like Chris showed you, the Zonotip does that for you automatically, very simply and very easily. And it's all about like achieving what you need to achieve in a very quick and timely manner. Okay, next application we've got for you is defining possible cracks and flaws.
Move this out of the way. I've got a plate here which has a pre-manufactured delamination in it, for example. So what you get is you get your normal reading of your thickness of the plate, and you can scan along, and as you get a delamination, you can see there, we're scanning over the delamination now, it's giving a reading of 12. The normal thickness of the plate is 14.8, but as we move over the delamination, we get a reading of 12. So that means we've got a defect. Let's see if I can find that again. There we go. It's over there. So that means we've got a delamination 3 millimeters away from the back wall surface. And you can use the A-scan, we don't have so much time here, to really characterise and size that defect if you bring the gain down, for example.
Fantastic. Thanks, Chris. One of the real cool examples that we gathered for you was the sample that I actually brought from UK. And me and Chris were talking together. It was actually last week, and we really want to kind of cover an interesting application. As you can see, there's a like, let's say, imagine there's a lamination or a flaw in this thing, and it's easily visible. If I flip this over, we assume that we don't know about this, but we want to obviously plot an area for this particular sample that we got here and find out what it is. So if you define like a, let's say, grid size on this, and put the device into the memory mode, what we're going to do, we're going to start testing from the side. And as we do the measurement, we're going to store along our grid every single measurement that we do. As you can see, as I'm moving along, the thickness is changing. So again, I'm going to move ahead, carry on doing the test on this grid, and you can see how the thickness readings are changing along my sample. We will obviously carry on doing the test for the entire sample. When the testing is done, we'll take our Zonotip device back, let's say, to our office. Extracting the data would allow us to then plot a graph. We can plot the data in, like, let's say, A scan, B scan, or a C scan, couldn't we?
Yeah, so a B scan is effectively a cross-section of your component. A C scan is a plan view, and what we've shown here is an isometric view. How we created these, it was very simple. You just get the results, which are comma-separated numbers, and you can plot them in Excel. And then you simply create a graph using Excel's inbuilt functions. And here, the importance of this is really to visualize what you're seeing in the component, and to communicate to any vendor who may not be able to understand an A scan, but they'll be able to see a picture of it, and it really helps with visualization there.
Absolutely. I mean, and this was, for myself and for you, it was a very, very good practice, and it was, like Chris said, quick, easy to generate such thing, and by looking at something in this sort of visual manner, that really, really helps. So that brings us to the end of our application. We're just briefly going to go through some sales and services side of things for you. One thing that we would like to highlight, as you're probably aware, at Proceq we have 8 regional business units, our series of subsidiaries and partner networks across the globe. Zonotip, the same as all of our other instruments, comes with 2 years electronic warranty on the electronic components. So you can extend that to 5 years, i.e. add an additional 3 years to it as an option. Our subsidiaries and certified service centers globally offer local services, traceable calibration, so on and so forth. So if you need more information on that, feel free to contact us, and we will put you in touch with the closest certified service center as well to take care of your instrument for you. And second thing I'd like to highlight here is that, especially in 2015, we have invested a lot of time and effort in the digital domain, making sure that our literature, our documents are always up to date. So I personally use our FTP server to synchronize my laptop, especially when I'm traveling, knowing that I always have the latest documents with me. You may choose to use an iOS device. Again, you can synchronize your device, or Android. The instructions is actually available online, and we have done some tutorial videos on our YouTube channel as well. In fact, I believe this webinar will be recorded and later uploaded to our FTP server as well, where you should be able to go ahead and watch it again if needs be. So on that note, I think we're going to have a quick conclusion with Chris on what we covered today before we start taking some questions. I mean, the key here is when we're looking for particular features, we need to identify them first, whether we're looking for thickness, bonding status, lamination, so on and so forth. And based on the type of information that we need to identify, we need to input certain properties. That could be obviously the material type. We highlighted how important it is to do your material velocity. And
it doesn't just depend, it's not just a technique for metal. You can use glass, rubber, plastics. It can be used for many materials.
Absolutely. As long as you have a reference block similar to our step blocks that you have over there, that you are able to measure the thickness of it. One thing to highlight here, we covered how geometrical aspects are important based on what transducer size you end up using. Accessibility that you have, that again dictate what sort of transducer you end up using, the location and extent of the flaw that you're looking for, and environmental conditions. Temperature is obviously a big factor, and based on that you should be able to choose your frequency and adjust your gain. One thing to highlight here, with Zonotip you actually can adjust the gain of the transducer, especially in the A scan mode, to move it to perhaps move it to hit the gate, or vice versa, move the gate around. So you need to play around with it and which one of them actually helps you better. And we highlighted again like the grid size in the last application. So it's following such steps obviously gives you greater accuracy and characterization, doesn't it, Chris?
Yeah, so for example, about a year ago we had this customer contact us in Austria, and they were trying to inspect this plastic pipe here, which, if you can see clearly, it has some copper wire in there, and what they wanted to measure was the distance from the back from this surface to the wires, just to see if they were the correct distance away. Now, what you would usually suggest is, because this particular plastic is attenuative, to use the lower frequency probe. What we ended up using was the twin crystal higher frequency probe, because it had better resolving power from the back wall to this. And yes, and then we solved the problem. And
yeah, and that goes to show you have to, a lot of time, the material dependency dictates what you really have to try different transducer physically to see which one fits it better.
And there's really no one solution to all thickness checking.
Absolutely.
You have to consider a lot of factors, and that's quite important. And we can help you with that.
Absolutely. I mean, we highlighted it before. I mean, we can emphasize it again. If you have application questions, feel free to contact us, webinar@proceq.com, or contact your nearest subsidiary. So on that note, I would like to thank you for joining us at this webinar. And what we'd like to do, we're going to start looking at your questions now. And between myself and Chris, hopefully we'll be able to kind of answer them all for you. And bear in mind, to ask questions, you can also unmute yourself by sending us a quick message. And we will unmute your microphone, and you can also ask your question via the audio system. I have already got some questions here, which we are going to look at. Okay, there was one question here about why it's so important to zero the device before start using it.
Yeah. Okay. So really, the 0 point is to tell your measurement where 0 is. So if you're making a thickness measurement, you need to know where your start point is, really, and that's what this panel on the front of the Zonotip does. And it's material independent. If you're testing glass or if you're testing rubber, you can still use this front panel. This is not the correct calibration.
Okay, thank you, Chris. The other questions I got here is, does it matter what material is the coating for true coat measurement? I mean, it doesn't, does it? You can go with paint, rubber,
I've used it a lot on paint. This is one of the only examples I've seen with plastic, which is from the oil and gas industry, but I've seen that.
Generally, paint is the most common true coat measurement application.
There's another one there. How often do you calibrate? That's quite a good question. Usually in standards, you say you do it at the start
Every
and end.
time.
Definitely at the start and the end of every shift. So you make sure that throughout your inspection, your results have been consistent. Now, if anything changes in between this start and end of the shift, then you have to recalibrate. If you disconnect the probe, for example, and so on, or if the temperature's changing, or
Absolutely.
anything like that, it's best to recalibrate.
I mean, one of the things that we're not supposed to be doing, but during the preparation of this webinar, we were actually testing our samples here, and it happened because we had several different units, and once we disconnected the probe and did not zero and recalibrate, and we were confused why our results are not working. And that just shows the importance of zeroing and recalibration anytime you disconnect and reconnect a particular probe. Okay. Please use the Q&A box for your questions if you have any more questions. Or on the other side, like I said, if you like to ask your questions via audio, please let us know and we will unmute you. Okay, I think that sounds like we covered everything. So on that note, once again, I would like to thank you all for participating in our webinar today. And I would like to also thank my colleagues at the back who made this all happen, took care of all the setting ups and the technical matters for us. As we end the webinar and you leave the room, there will be a quick survey that pops up. We would really appreciate if you could spare a minute or so to fill in the survey, give us your valuable feedback, because that would really help us to fine-tune our future and upcoming webinars that we're planning for you in 2016. And so on that note, thank you very much and goodbye from me.
Yeah, and thanks for your time and goodbye.
Thank you.